In this video and the next video, I'm going to give just a brief introduction to the Ricci curvature tensor and the Christoffel symbols. And then the video after that, I will talk a little bit about the stress energy tensor, both of which are important in the Einstein field equations of general relativity. So this R here is the Ricci tensor, which is a rank 2 tensor. This R here is the Ricci scalar, which I will also talk about in this video, and the Christoffel symbols that are actually found from this G here, which is the metric tensor. Same with this G here. This uppercase lambda is actually the cosmological constant, and that has to do with dark energy. And so this part right here is oftentimes called the Einstein tensor, and you will often see that as a G, so as a capital G mu nu. And so its components will be the components of the Ricci tensor minus 1/2 times the curvature scalar there times the metric tensor. And I'm not going to get too much into like the derivation of all this. I mostly just once again want to give an intuition of each of these things. As usual, there are links in the description where you can really start digging into these things quite a bit more. But for this, I am just going to give kind of a really brief, basic overview so that at least if you see this equation, this Einstein field equation, you kind of know what each thing is talking about. So this T over here, this second rank tensor, is the stress energy tensor. And so the way that this equation is often thought about is on the left side of the equal sign here, we have the geometry, so the differential geometry. Then on this side, on the right side, we have the part that talks about the mass and the energy. And so the left side is oftentimes said to tell matter how to move, while matter tells space-time how to be shaped or how to bend or flex or so forth. And so down here, so just to give you a little bit of an idea, so this is called the Schwarzschild metric, and it's in spherical coordinates. So this is a metric tensor, and we see that it has this minus 1 minus 2gm over rc squared. And then this is the same thing, but it's inverse. Then we have this r squared and r squared sine squared theta, which should look familiar from when we're using spherical coordinates to actually look at a sphere. And so it'll actually give a space that looks sort of like this. And so we see we're flat, and then we sort of in a symmetrical sense, we then start falling in down towards over here. There'd be the singularity of a black hole. And actually, with this Schwarzschild metric in spherical coordinates, the Ricci tensor, I believe, is actually 0. So you'd need a different metric, so a metric describing something else than this to start looking at that Ricci tensor. But this is just to get sort of an idea of what a metric would look like in general relativity. All right, and so the first thing we have is this Riemann curvature tensor, which is used more in things like differential geometry, and that's actually a rank 4 tensor. And so, well, actually here I just have a rank 2 tensor that I'm contracting down to, well, a rank 0 tensor. But what we would actually want to do is this, which is taking this rank 4 tensor, which has one upstairs index and then three downstairs indices, and then contract it. So we keep the upstairs one I, and we change the downstairs one to I, and then we sum over the I, and then that will actually get rid of the two I's, and we will end up with something like R RHK, and so that looks more like what we want. So if we look here, that has two downstairs indices. And so to contract that, like I said, we are going to sum over I for every value of H and every value of K. And so if we have H equals 0 and we run through K equals 0, 1, 2, and 3, we end up with this. And then we have H equals 1 and we want to run through K equals 0, 1, 2, and 3 again. And then we do it again for H equals 2 and then again for H equals 3. And I'm not going to sort of talk through all of this. The thing to really notice, though, once again, is why we like that Einstein summation convention. And so that is why you will see it mostly looking just kind of like this, even without this summation here, that implicit summation when we have two indices that are the same. And so we just run through all of those, and then these that I have here on the right side of the equal sign, I have now put into a matrix that looks like this. And this matrix works because if we tried to do the Riemann curvature tensor, which is this 4-index thing, we'd need a 4-dimensional matrix, and that would be quite difficult to try to draw, which is one of those reasons that people who are more rigorous will say that will try to often steer away from this matrix representation of tensors. But I like the matrix representation. I think it makes it a little more intuitive what's going on. But yeah, since this is only a rank 2 tensor, we can actually draw it in this matrix form. And you can see I put in blue all the ones that are on the diagonal. So the 0, 0, the 1, 1, the 2, 2, and the 3, 3, which all go into the diagonal of this. And essentially what we're doing, and I kind of gave it away up here when we're contracting a rank 2 tensor, is we're taking the trace sort of the rank 3 tensor, or kind of a trace, because you can see there'd be all different kinds of quote-unquote traces we could take by summing over that one instead of that one, and so forth. Where the trace thing works better with a rank 2, since we're just summing over the ti and the ti. So it's just t11, t22, t33, and yeah, this one I only did a 3-dimensional rank 2 tensor, but you see we're just adding all the diagonals on here, and so that is just the trace. So this is kind of like doing the quote-unquote trace of a rank 4 tensor in order to generate this rank 2 tensor. Well, and then so if we want to get that Riemann scalar, well, the first thing we have to do is we actually have to raise one of these indices, because we can only sum over an upstairs and a downstairs. And so we actually do the index raising, which I talked about in a previous video, in order to sort of raise this mu up to a sigma here. And to do that, so we just do this matrix multiplication here. And so I just kind of put here what matrix multiplication is. So to get this element here, we actually have to multiply A1 times B1, A2 times B2, and A3 times B3. Then to get this one, it'd have to be A1 times B2, A2 times B5, and A3 times B8, and so on and so forth. And so that's what I actually have showing right here. So this is just looking at how we get this first element. And then if we just go through and do all the elements, we end up with something that looks like this. But anyway, I went through that in more detail in an earlier video of how to actually raise and lower indices. So I'm not going to go through that too much here. But anyway, the first step is to raise the index, and then we want to contract, which once again is just kind of doing the trace here. So just these, we're just adding these blue R's here, and so that's how we actually get this this Ricci scalar here. So I'm editing this in because I realized that after I recorded, I forgot to say what the scalar curvature or Ricci scalar means. And so what it means is essentially if you have some circle in space here, a circle in 2D space, the area, that's a really bad circle, I'll try and draw it a little bit better. So in a circle in 2D space, we have the area of the circle is just everything between these lines here. But if we have curved space, then we have a circle, and so the space will actually sort of stick out. So so everything in between the circle will sort of stick out. So it looks kind of like a little yarmulke or something. So I'll try and draw it a little bit from the side. And so it would actually have sort of a dome on it. And so the area of that circle is going to be larger if it's bent, because now we have to account for all that area rather than just the area directly between sort of the border of the circle. And so that R is telling you sort of how much there's a bulge in our circle. And so that's what the scalar curvature is actually telling you, geometrically speaking. But anyway, this, like I said, was edited in after I finished recording the video. So now back to our regularly scheduled program. All right, and then so in the Ricci tensor, so this is the Ricci tensor, and I'll talk a little bit in a bit more detail about this in the next video, but I'll just introduce it here. And by the way, these figures that I have here, so from here going all the way up to here, all came from this website, which is it's not a video, it's something you have to read, but I found it a really great resource for understanding the Ricci tensor. So if you want to dig a little bit deeper into it, then I would highly recommend checking that out. And I'll leave that link in the description down below as well. And so each element of the Ricci tensor, so up here we just have it with these R's, but each element is actually this long thing here, with all these uppercase gammas and some of these partial derivatives. And so those gammas are the Christoffel symbols, and each gamma is this. And we see that we have these metric tensors here. And if you remember, the metric tensor just has the bases in it. So so for instance, if we had a metric tensor for 2 dimensions, so ij, that's just the e1 dot e1, e2 dot e, or e1 rather, e1 dot e2, e2 dot e1, and then e2 dot e2. So it's just the dot products, it just says the dot products of the basis vectors. And so this is sort of like a derivative of the basis vectors. And so the reason we'd want a derivative of the basis vectors is because if we're in a space that is not flat, then so you will have at this point, some basis vectors here. So if this is like 3 dimensions, but space is curved, so you'll curve down, you'll end up with basis vectors that is more like this, where this is our z, x, and y. This is our z, x, and y. And so this z here has changed. So we've gone from having z here, so maybe we'll call this prime, z prime, x prime, y prime. There's some change. There's an angle change here in our z. And so that's, and of course also in the x and in the y. So those things all change. And in general relativity, we're actually talking about changes of 4 basis vectors, since we're talking about 4-dimensional space-time. But what these Christoffel symbols are telling us is essentially, so we have this sort of weird shaped space here, and it's telling us if we start at this point here, and we move to this point here, and then over to this point here, we will have, our basis vector will have changed in, so that we are pointing this way, whereas say we move from this point here down to this point here and then up to this point here, our basis vector will be pointing that way. And so this change in the basis vector here, and this is actually the Riemann tensor. The Ricci tensor is the contraction of that, but the Riemann tensor, so it's showing us, some change, some difference in those vectors there, depending on which path we actually take. And the path we take is going to change it because of the way that space is bent. And so the other way you can think about it is that the Ricci tensor, and so this is actually the Riemann tensor. The Ricci tensor is telling us essentially how much the 2 geodesics here change. So if we moved, say, from like right here to right here, it's telling us, how much these geodesics have actually moved away from each other. And so if we have like geodesics that are going like this and sort of separating, it's telling us essentially if we have like a ball here, how much the volume of that ball has changed. Or if we have geodesics that, sort of bend inwards like this, we have a ball here and it's telling us how much the volume of that ball has shrunk. And so that is what the Ricci tensor is telling us. So describe how much the space-time volume between the geodesics change in each direction as the geodesics begin deviating away from each other. And so here, so this once again is still from this this profound physics website, and I liked this because it's the general steps for calculating the Ricci tensor. So specify a metric tensor. So we calculate those Christoffel symbols from the metric, which then we can use to calculate the components of the Ricci tensor. And like I said, in the next video I talk a little bit more about these Christoffel symbols. But here we have a Ricci tensor. So this is with the summations explicit on here of the Ricci tensor. So I just took this here and made the summations on each of these things explicit. And so we have this Christoffel symbol, these Christoffel symbols here, or the derivatives of these Christoffel symbols, and then these products of the Christoffel symbols. And then I just wrote the Ricci tensor with all the Christoffel symbols explicit into matrix form here. And once again, you can see how big and crowded things get. And so that is why the Einstein summation is preferred. And so down here I have the Christoffel symbol at the so at this first part right here, sort of written out explicitly. So outside the Einstein summation convention. So we're adding this and this and then this and this. But anyway, that is a little bit about the Ricci tensor. So the main things to take away, like I said, are that the Ricci tensor is the contraction of the Riemann curvature tensor, and then that Ricci scalar is the contraction of the Ricci tensor, which is a rank 2 tensor. And then the other part is just this idea that the Ricci tensor is telling us how volumes between geodesics, which are straight lines in space. I mean, you see these and it's like, well, that's not a straight line. Well, it's a straight line, but through bent space. So it's space itself that is bent, not the straight line. So you may have heard of geodesics if we have our planet Earth here, and we want to, go from one place to another. You don't just do a straight line. You have to do one of those sort of great circle things over it, and that's because that is a straight line on sort of the bent surface of the Earth. And so these, even though these lines look like they're bent, it's actually the space that is bent, and the lines, the geodesics, are sort of the straight lines through that bent space. And so by looking at how a sphere or a circle sort of changes in volume between two geodesics tells you something about how much the space is bent. But anyway, I hope you found this video helpful, and in the next video, like I said, I will talk a little bit more in depth about the Christoffel symbols and sort of how to intuitively interpret those. Yeah, anyway, I will see you in the next video.